yeah. Hmm. Okay. Keep this here for now. So, hello. Yo. Um, let's see. Alright, how does it sound now? I hope it sounds okay. So I'm just gonna study for a couple hours. Bitrate, huh? $13,500. What? Mm. think we're good now. So I think first of all, I gotta do my I don't know where my water bottle is. Oh. Shafi, can you come here? Can you fill up this bottle? I'm streaming. Yeah.
Still streaming?
Yeah. No, you're not playing tonight. Thank you.
of elements in it. Current has a number of them, starters has a number of them, WO3 has a number of them. So it can be arbitrarily wide. In addition, the structure can be arbitrarily
Yo,
arbitrarily deep. This particular in it, curves which were arbitrarily long in one dimension or arbitrarily wide in one dimension. This arbitrary array tree is arbitrary sized in two dimensions. A given folder or directory like W03 can have an arbitrary number of elements in it. Current has a number of them, starters has a number of them, W03 has a number of them. So it can be arbitrarily wide. In addition, the structure can be arbitrarily deep. This particular one is 1, 2, 3, 4, 5 deep, but it could be deeper. Remember, arbitrary doesn't mean large and it doesn't mean random. It just means that before we start out, we don't know how big it will be. Now, in order to deal with this arbitrary sized in two dimensions structure that this has, the key thing that we're about to see is that it's going to require two cycles in the type reference graph. Remember, in order to have an arbitrary sized list, we had one self-reference cycle in the type reference graph. Here we're going to see that we end up having two of them. So now let's turn to Dr. Racket and start looking at that. Now I'm in fsstarter.racket, and what I have here is the beginning of two data definitions that can be used to represent arbitrary array trees like this one. So first is a structure definition, ELT, which has three fields, name, data, and subs. And of course we have to keep reading to know what that's about. And there's a type element, and it says element is a make element string integer list of element. And an element is an element in the file system. So that's going to be something like, from our picture, MOOC or current or lecture exercises or starters. And what I'm saying here, because we said in the analysis that an element could either have sub-elements or it could have data, I'm saying here that there's data, which can be an integer, and there's subs, which is going to be an arbitrary number of elements. And it says if the data is 0, then subs is considered to be a list of sub-elements. If data is not 0, then subs is ignored. There are other ways to do this, where instead of having an element have both fields, in other words, both data and subs, you make two different kinds of elements. I thought this was simpler for our purposes for now. And then what's list of element? Well, list of element is just an ordinary list of type, like we've seen several times now. It's just a list of file system elements. Now let's see if this can build up the structure we want. So what I'm saying here is F1 is an element called F1. It has a non-zero data, so it's like an ordinary file. That's why I called it F. And its subs are supposed to be empty. Its subs are ignored, basically, so I just put empty. So that's F1. F2 is just like F1. It's another file. It happens to have the contents or the data too. And F3 is the same. Now what's D4? Well, D4 has 0 for the data, so that means we're going to pay attention to the subs. And what subs does it have? Well, it has two subs, F1 and F2. So that looks like this.
because I already did.
And then D5 has a single
25.
sub, F3. And then D6 has both D4 and D5. So that little set of examples there builds up this directory structure here. And I think we can see now pretty clearly, it looks like we can build an arbitrary array tree here. Let's see why that is. Well, if we look at list of element has a self-reference in it. And that's what's allowing a directory's list of sub-elements to be arbitrarily long. That's what lets this list have F1 and F2, and this one have D4 and D5, and clearly those could be as long as they want. Now, in addition to that self-reference, notice that there's a reference here from the middle of the list of element type back to the element type. We've seen that kind of reference before, but hang on, because there's something else going on here. There's also a reference from the element type down to list of element. Now those two references together form what's called a mutual reference. So we're going to label them MR, because you can go from the definition of list of element up to element, and the definition of element down to list of element, and there's a cycle there, a mutual reference cycle, same. Now what's D4? Well, D4 has 0 for the data, so that means we're going to pay attention to the subs. And what subs does it have? Well, it has two subs, F1 and F2. So that looks like this. And then D5 has a single sub, F3, and then D6 has both D4 and D5. So that little set of examples there builds up this directory structure here. And I think we can see now pretty clearly, it looks like we can build an arbitrary array tree here. Let's see why that is. Well, if we look at list of element has a self-reference in it. And that's what's allowing a directory's list of sub-elements to be arbitrarily long. That's what lets this list have F1 and F2, and this one have D4 and D5, and clearly those could be as long as they want. Now, in addition to that self-reference, notice that there's a reference here from the middle of the list of element type back to the element type. We've seen that kind of reference before, but hang on, because there's something else going on here. There's also a reference from the element type down to list of element. Now those two references together form what's called a mutual reference. So we're going to label them MR, because you can go from the definition of list of element up to element, and the definition of element down to list of element, and there's a cycle there, a mutual reference cycle. So in addition to the self-reference cycle, which is letting one directory have an arbitrary number of immediate subdirectories, the mutual reference cycle between list of element and element is letting that be arbitrarily deep. So D6 can have an arbitrary number of subdirectories, D4 and 5, and each of those can have an arbitrary number of subdirectories, and so on and so on and so on. And so what you can see here is that these two cycles in the type comments, the self-reference cycle and the mutual reference cycle, support an arbitrary arity tree, a tree that can be arbitrarily deep and arbitrarily wide at any point. One quick note about these arrows and the way you label mutual reference arrows. The way I do it is first I draw all the arrows. Then I label all the self-reference arrows. Then I put my finger on an arrow and I start following it around through the types. And if I ever come back to that same arrow, then all those arrows along the way were part of a mutual reference cycle. And then any arrows that aren't part of a mutual reference cycle and aren't part of a self-reference cycle are just ordinary reference arrows. In this case, where there's just two types, it's easy. But sometimes you can have mutual reference through 3 or 4 or 5 or 6 or more types. And then it's a little harder to get the arrows right. It's very important to get them right. We're going to see it helps us a lot with the templating that we'll do in the next video.
I started using my notebook ever since February 20 to do my to-do list. That's why there's like a gap here. But I'm just doing it out here so we have something. This is the coding series.
In the last video, you saw the type comments for an arbitrary arity tree, and you saw how the mutual reference works in those type comments. Because of the two cycles, the tree can be arbitrarily wide at any point, and it can also be arbitrarily deep. You have now seen the most important part about arbitrary arity trees. In this video, we're going to do the templates, and there won't be any new template rules. The templates are just going to fall out from what we already know. So now I'm back in fsstarter.racket, and again, we've got the two types which have mutual recursion, and we're going to do the templates. And the interesting thing we're going to see about the templates is we already know how to do them. Just a reminder, when we have types that involve mutual recursion, what I do is put each type and interpretation together. So there's element and its interpretation, list of element and its interpretation. Then I put all the examples, and now I'm going to put all the templates together. And that's going to be much easier for us when we go to design the functions, and it also helps us see the mutual reference structure better. So here we go. There's going to be two templates because there's two mutually recursive types. So there's going to be that template and that template. And let's see. Notice I'm not putting the template rules used because you're not required to do that anymore, but I'll talk about them as we do it. This is a compound data, so there's all three selectors. And then I'm going to decorate that with the types of value that come back from the selector. So in the case of name, it's a string. In the case of data, it's an integer. And in the case of subs, it's a list of element. Now, list of element is a non-primitive type. It's a type that we defined. So the reference rule here says that we should wrap this selector into a call for fun for LOE. And I'm going to go ahead and do that like that. Now we're done with fun for element. For fun for LOE, well, let's see, this is a one of with two cases. So there's a con with two cases. First case is atomic distinct empty. Second case is the second case, so we'll say else. Then it's a compound cons. First LOE, rest LOE. For a second, we'll just decorate those. Well, this is an element, and this is a list of element. The reference rule here says that we'll wrap this in fun for element. And the self-reference rule here says we'll go fun for LOE. So there we go. We've got the template for both types. And we didn't really need a new template rule. The reference rule and the self-reference rule just work to produce the right answer. In some sense, the only new rule for templating types involving mutual reference is to do both templates at the same time. That'll help you see the mutual recursion structure in the templates corresponding to the mutual reference structure in the types. And just to draw that out for you, let me switch again to this kind of figure that we've seen before, where I've got both the type comments and the templates. And you could see where there's a self-reference, there's a natural recursion. Where there's a mutual reference cycle, there's a natural mutual recursion. So fun for LOE calls fun for element, and fun for element calls fun for LOE. And in the next video, we'll see how that plays out as we're designing the functions.
I made 3 sandwiches and a bowl of beans. Chubby bowl. No. Chubby.
Oof, Shafi, you just gonna walk around my room like that?
It's okay. THE.
Cool.
Yeah. What's that?
Now we're going to design functions operating on arbitrary arity trees. And what we're going to see is that even though mutual reference in types is the most complicated data we've seen so far, the function design is pretty straightforward. It falls out from what we already know.
What?
Now that we've got complete data definitions for mutually recursive types, the data that's going to represent the file system structure for us, now we can start designing functions. And the thing that's going to be pretty cool here is designing these functions is actually going to go very smoothly and easily because of all the method we've learned so far. Here we go. I'm in fs-v1, and in this version of the file, this is just the file we had last time, except that I went ahead and added a little picture of this directory structure, because that's going to make it easier to design functions. If I had just been working by myself, I would have scrawled that out on a napkin or something. But I popped it in there for you. And also, there's 4 function problems. I'm not going to do all of them. In this video, I'll do just the first one, and I'll do another one, and then the other ones you'll do on your own. So here we go. We're going to design a function that consumes element and produces the sum of all the file data in the tree. So for example, in this tree, because the
break time.
data is always the number for a file. If we sum this entire tree, well, that data is 0 because it has subs. That data is 0. That data is 1. That data is 2. That data is 3. So 1 plus 2 plus 3 is 6. That's the function we're trying to write. So let's go ahead and follow the method and do it. Now, the key thing is when we design functions that operate on mutually recursive types, when the data has mutual recursion in it, we design multiple functions at once. So here I know there's 2 types that involve mutual recursion. I'm going to do 2 functions right away. So I'm going to write element to, let's see, I'm adding up the data, and the data is always an integer, so this is going to be a sum of integers. So that's element to integer, and also list of element, because remember, I'm going to do both types, to, well, I don't know what this is going to be. It might be integer because that's what element produces, but it might be something else sometimes. Oftentimes it's the same. Both mutually recursive functions produce the same type, but not always. So that's why I put those question marks there, to remind me to come back and check that. Now I'm going to say produce the sum of all the data
You're not playing today, bro.
element and its sum.
Yeah,
I'm writing the purpose for the first function. I'm writing the purpose for the function that consumes element, because that's what I was asked to do.
Go to school.
Now I'm going to do 2 stubs, and I'm going to call this function sum data. Except there's not going to be one function, there's going to be 2, right? There's going to be the one that consumes element and the one that consumes list of element. So the naming convention I'm going to use is like this. I'm going to say sum data dash dash element. That's the one that operates on element. The stub for that is 0. And sum data dash dash list of element consumes list of element, and the stub for that is probably 0. We'll come back to that. Now let's do some check expects. Check expect sum data dash dash element. Now there's recursion involved, so we should start with a base case example. And when you've got mutual reference, it's not clear quite what is the base case example. There tends to be more than one. Well, one example is sum data dash dash element of f1. That's just, you know what I'm going to do? I'm going to go up here and get this figure and bring it down here temporarily. I'll just bring a copy of it right here so we can refer to it as we work. And then we'll just delete it later when we're done. Sum data dash dash element of f1. f1 is a file for which the data is 1, so that produces 1. That seems like at least a close to base case example because f1 has no subs, so there's no recursion there. Another base case example might be one that we don't quite have in here, but sum data dash dash list of element of empty. Well, what's the sum of all the data in an empty list of elements? Well, that's 0. Now let's try to do the next simplest example I can think of, which is sum data dash 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 element of D5. That's pretty simple because D5 only has one sub. Well, the sum of all the data in D5, remember, things that have subs don't have data. So the actual value there is 0, so that's just 3. And let's do sum data of D4. Well, that's also 3 because 1 plus 2 is 3. That's plus 1 and 2. And then let's do the top one too. Sum data of D6 is, what is it? Well, it's 1 plus 2 plus 3. And now it's really starting to look like sum data LOE has got to produce an integer because there's sort of this meaningful notion of what's the sum of all the data in an empty list of elements. So this is really starting to look like it's going to be an integer. But let's keep going. Okay, signature, purpose, stub, examples. Let's go get the templates. Here's the templates. I had also commented them out so that they wouldn't get highlighted in black when we run the program. There they are. Now we'll comment out the stubs. We'll uncomment the templates. And when you've got mutual recursion, you really need to be careful about the renaming of the templates. So fun for element is going to be called sum data dash dash element, and there's a mutually recursive call down here that I need to be sure to rename as well. And fun for LOE is going to be called sum data dash dash LOE, and there it is, and there's its recursive, its natural recursion, but here's the natural mutual recursion. So you need to be sure to name the mutual recursions as well as the function definitions and the self recursions. Okay, let's see. I want to sum the data in an element, and the interpretation, remember the interpretation is that if data is 0, then subs is considered to be a list of sub-elements. And if data is not 0, then subs is ignored. So to know how to interpret a given element, we need to look at data first. We need to know, is data 0? Well, let's start by doing that. It doesn't look like name has anything to do in this function, so I'll just get rid of it. And I'll start with if 0 is the data 0. Now, if the data is 0, it means I'm supposed to go look in the subs to see how much data is there. So I'll leave the natural mutual recursion to do its work. If the data is not 0, then this element is a file. It has data. So we're going to produce the size of this data. Now let's look at sum data LOE. Well, the sum of an empty list of elements, intuition plus this example here, tells me is 0. And otherwise, now when you've got mutual recursion, you've got in a big way trust the natural recursions. You've got to trust the natural self recursion. You've got to trust the natural mutual recursion. If I've got a list of elements and I have the first element in my hand and the rest of the elements in my hand. What's the sum of all the data in them? Well, it's the sum of the data in the first plus the data in the rest. This just becomes a plus. Because I'm trusting that this thing is going to do what it said it would do, and this thing is going to do what it said it would do. And now it's really clear here, now that I have this plus, and also I'm returning some data LOE here, this really is integer. We're counting on the list of element function to produce the same type of result.
Oh, hold on. I see. It'll be like this plus
as the element function. As I said, when you have mutually recursive functions, it's usually the case that all the functions produce the same type of data, but there's some exceptions to that rule. So there we go. We filled in all the dots. What happens? So let me save it and try running it. All 5 tests pass. Now, you may have a little feeling there like you had the first time we wrote a recursive function. Why did that work? And the reason it worked is we had these well-formed self-referential type comments. There was always a base case. And that means we got templates derived from that that supported natural mutual recursions in the right place and that have a base case right here. We formed our examples carefully and systematically. We coded to them. And we get a mutual recursion that has the right structure and that always terminates in a base case. So again, what you're seeing here is that the way the method works by being data-driven in terms of getting well-formed self and mutually referential type comments to the templates, coding those to complete the functions, trusting the natural recursions, that makes functions like this quite easy to design. What I'd like you to do now is do this next problem, where you design a function that consumes element and produces a list of the names of all the elements in the tree. So that was pretty straightforward. Coding those to complete the functions, trusting the natural recursions, that makes functions like this quite easy to design. What I'd like you to do now is do this next problem, where you design a function that consumes element and produces a list of the names of all the elements in the tree. So that was pretty straightforward. The key point really is that when you design functions operating on mutually referential types, you don't design a single function, you design one for each type. And so it pays to group the signatures together, to maybe write a single purpose, to group the examples, and then group the functions. That makes it easier to work on them. Another issue has to do with the examples. These are mutually recursive functions, so you want the base case first. But sometimes it's a bit more natural to put a case that's one away from the base case first, as it was in this case. It's worth noting here that the method we're presenting in this course is really starting to pay off here. In a lot of other approaches, functions that operate on trees would be very different from functions that operate on lists. It wouldn't be the natural extension it was here. Really, the only thing we learned in the latter part of this week was mutual reference and type comments. After that, we really knew how to complete those data definitions and write those functions. I think that's pretty cool. In this video, I'm going to design another function operating on element. Remember that element and list of element are mutually referential types, and so that means designing one function is actually going to end up designing two of them. I'm in fs2-v2.racket, and if I scroll down here to the problem, here it is. Design a function that consumes element and produces a list of the names of all the elements in the tree. So I know right away it consumes element, and I need to know what list of names means. So I'll go back up to the element data definition. And let's see, for an element, the name is a string. So this is going to produce list of string. And of course, there'll be the function that operates on list of element. And that's almost certainly going to produce list of string as well. Let's do a purpose, produce list of the names of all the elements in the tree. We'll do a couple stubs. All names dash dash element, which consumes E, produces empty, and all names dash dash LOE, which consumes an LOE, produces empty also. So those are the stubs. Run them to be sure they're well formed. They are. There's no test, so they're not running, so they're highlighted in black. Okay, let's do some examples. Check, expect, all names dash dash. Now, which one should I test first? Well, let's go look at the type comment. Up here at the type comments, what we're looking for is what is the base case. Remember, the base case is a place where the reference cycles stop. It isn't here in element because the only thing that happens in element is make elt of these three fields, and list of element is a reference to list of element. So let's look in here for the base case. Well, here we see that the base case is operating on an empty list of element. Because this isn't the base case, the cons case isn't the base case. That goes in a cycle to list of element, and it also goes back up to element. So an empty list of element is the base case. So now we can go back down to where we're working, and we know that to test the base case first, we're going to start with all names dash LOE of empty. What does all names of an empty list of elements produce? Well, that sounds like empty. We're still not quite certain that this function is supposed to produce list of string, but assuming it is for now, it would clearly produce empty in this case. Let's do another case. We've done the base case, but let's also try to do a simple case now. And what I'm going to do is go back up here and get this figure and copy it down here. It's really great that Dr. Racket lets you do this. You should enjoy it now because not every programming environment will let you do it. So we've tested the empty list of elements case. Let's now check all names dash element of, let's check F1. Well, what are all the elements in the tree starting at F1? Well, it's just F1 because F1 has no sub-elements. So all the names are list F1. All right, let's check another case. Let's check all the names in D4. Well, what are all the elements in D4? Well, there's D4, F1, and F2. So those are the names, D4, F1, and F2. Let's do another one. See, we've done F1. There's no use doing F2 or F3 because they're the same as F1. And there's really no use doing D5 because D5 is simpler than D4. Except maybe we should have done D5 first because it's simpler than D4. It's not much simpler, but it seems a little simpler. So let's do it. And it would produce, what would it produce? Well, it would produce D5 as the first thing and F3 as the second. And now what's D6 going to produce? Well, let's see. D6. Well, D6 has D6 in it for sure. And what else does it have in it? Well, it has everything in D4, which is all of that, and everything in D5, which is all of that. And let's see. These two lists have to be combined, and that has to be put on the front. So one way of saying that is appending those two lists together and consing that single item on the front. You could, of course, just write the value. You wouldn't have to write the elaboration. So you could just write it this way. But the elaboration might be helpful, especially for a case a little bit complicated like that. Okay, let's run it. All names-element is not defined. Oh, I didn't follow my naming convention properly. And since I cut and pasted, I didn't follow my naming convention properly several times. Okay, the tests are all well formed. Let's save this. It's always good to save often. Okay, so let's comment out the stubs, and let's go get the templates. And I'll show you a trick here. If you go right here, you get a list of every definition in the file. So as files start to get bigger, you can jump to individual definitions more quickly this way. And all good programming environments give you a feature like this. So I'll go to Fun for Element, and I'll grab the two templates. And I'll go back down where we were. And I'll get rid of these comments. I'll do the renaming. Remember, there's mutual recursion here, so I have to be careful to get all the references. There's that one, and then there's this natural mutual recursion here. And then when I rename the LOE function, there's the definition, there's the natural recursion, and there's the natural mutual recursion. So I get all those. So now let's work off the examples. The first example tells me that if I call all names LOE with empty, I get empty. The second example tells me that if I call all names --element of F1, I get F1. Let's see. In that particular case, this would be F1. And what would this natural mutual recursion be? Remember, I'm reluctant to delete natural recursions or natural mutual recursions. Well, it would be all names --LOE of empty because F1 has no subs. And we already know that's going to produce empty. And that seems kind of natural. It seems natural to just cons F1 onto the natural recursion. That's also what this very complicated example was suggesting to us, was that you would cons the first thing onto the recursion. At this point, it's really clear that this function, the one that consumes list of element, has to produce list of string, so I'll get rid of that set of question marks, and I might even do this. Let me get rid of this note. Let's see, I'm almost done. I just have this case. This is a case where all names LOE is called with a list of elements that isn't empty. And we don't exactly have that case. Let's put that case in here.
Hold on.
So let's say it's called with D4 and D5. Well, what's it supposed to produce? Well, it's got to produce everything in D4 and everything in D5 combined into a single list. And again, the way you combine two lists is with append. So that suggests that this should be append. Let's try running it. Check expect expects two arguments but found only one. It's telling me that this is the whole check expect, so that's not right. I've got an extra parenthesis there.
Yeah.
And whenever you have an extra parenthesis there, you almost surely are missing one a little farther along. There. Now let's try it. One of the tests failed. D4, F1, F2. So this produced, I'm just going to grab what it produced here. Because I've got my screen small for recording, I have to be a little bit careful here. I'll slide this down here. I'll click here to see what test it is. I'll reselect this. So in this test for D4 and D5, it produced, oh, I have them in the wrong order. I just have my test examples in the wrong order. Because I asked D4 and D5, but over here I put the order 5, 4.
Okay.
Let's save it and run it.
Class
All
assembly.
12 tests pass.
বিকালে
Let's
class
look at the
আছে।
whole function again.
Okay.
We'll delete this figure. Again, this was almost entirely following the how to design functions recipe that we've come to understand quite well now. The only wrinkle that came in because of the mutually referential types was that we had to design two functions. We had to think a little bit harder about what was going to be the base case test. We used a naming convention to have two functions of different names that operated on the mutually referential types. That's really about it. This is mostly an ordinary how to design functions problem with more complicated data. In this video, I'm going to design one more function operating on arbitrary arity trees. So much of this will be familiar, but the design of this function introduces a new and important concept called backtracking search. So let's go find the problem. It's in fs-v3.racket, and we'll scroll down here, and we're supposed to design a function that consumes string and element. Let me write that down, string element, and looks for a data element with the given name. If it finds that element, it produces the data. Otherwise, it produces false. It produces the data. Let's see what that means. So I'm looking in one of these trees for an element with a given name. I'll write this. If it finds a function that consumes string and element, let me write that down, string element, and looks for a data element with the given name. If it finds that element, it produces the data. Otherwise, it produces false. It produces the data. Let's see what that means. So I'm looking in one of these trees for an element with a given name. All right, the string is the name, so that's why I got the string as an argument. I'm looking for an element with the name equal to the string I was given. And if I find it, I produce the data, which is an integer. So going back down here to where we were, we're going to produce integer if we find it, and otherwise we produce false. So that's different. That's something we've never done before. What's happening here is this function is going to go look for an element with the given name, and sometimes it's going to produce the data, otherwise it's going to produce false. We've written functions that say whether a given string is in a listed string, but that function always produces a Boolean, true or false. Here we're going to produce the data if we find it, or false otherwise. And so we need a little extension to how we write function signatures to do this. And what you're going to do is you're going to say whatever type it would produce if it succeeds, or false. So this is a special form of signature that's particularly applicable to backtracking search. Now in some programming languages, in most recent programming languages, there's a more sophisticated mechanism called exceptions for dealing with this kind of case. To keep BSL simple, BSL doesn't have exceptions. But the basic way we're doing backtracking here can easily be adapted to a language that does have exceptions. So let's see, search the given tree for an element with the given name, produce data if found, false otherwise. Let's do some stubs. We're operating on two mutually referential types, so there's going to be two functions. Define find dash dash element, which will consume an element, but it will also consume a name, some string. And for the stub, we'll just assume it always fails, it'll produce false. And define find dash dash list of element, which will consume a list of element, but it'll also consume the name that it's looking for, false. Okay, so those are the stubs, and we should put the signature for the second function, list of element, string, and list of element. And again, we never quite know here for sure, but let's put integer or false. Okay, let's do some examples. Well, let's start with the base case. We know that in this case, the base case is the dash LOE function called with empty for the LOE. That's where the mutual reference and self-reference cycles all stop. So we'll say check, expect, find dash LOE. Let's say we're looking for F3 in empty, and of course we can't find F3 in empty. because there's not anything in empty at all, so that'll produce false. Now let's do another simple case. Let's say check, expect. Let's look for It's find dash dash LOE and find dash dash element. Let's say we're looking for something named F3. In F1. Well, that's false. There's nothing named F3 in F1. And most of these other tests are going to be find in element, so we'll make that something we can copy. Well, what if we look for F3 in F3? Well, if we look for F3 in F3, we do find it. We find it right away, because F3 is F3, and so we return the data, which is 3. Okay, so that's the base case and two very simple immediate success or immediate failure cases. Let's try to do another case. Let's look for F3 in D4. Well, that's false. We don't find F3 in D4. But what about looking for F1 in D4? Well, we do find that. F1 is the first child of D4, so this is going to produce 1. But what about a case where what we're looking for is not the first child of D4, but one of the later childs of D4? We should try that case, because it kind of corresponds to searching in a list and making sure we search beyond the first element. So if I look for F2 in D4, I'm going to find it, so the data will be 2. Seems like we should also try a case where we're looking in an element that has subs, but what we're looking for is actually the element itself. So let's see what happens when we look for D4 in D4. Well, anything that has subs has data 0. So this is going to produce 0. And let's try one more big one. Find dash dash element. Let's try looking for F3 in D6. That's the far right child, and that would produce 3. So that seems like a pretty exhaustive set of tests. Let's run those tests to make sure they're well formed. They're all running and most are failing, so they are well formed. And let's save that. Okay, now let's go get the template. 2 of them, of course. Here they are. We'll go back down to the function that we're working on. We'll comment out the 2 stubs, paste in the templates, uncomment those. Now do the renaming. Find element is that, and here's the natural mutual recursion. Copy that. Here's the function name, here's the natural recursion, and here's the natural mutual recursion. And there's one more thing to do here. These are functions that consume 2 arguments. They consume the element or the list of element, and also the name of the element we're looking for. So we have to add a parameter n there, and we have to add a parameter n there. And remember, I said whenever you have recursion, and it also applies for mutual recursion, when you add a parameter, you should be sure to go put a note to yourself at each recursive or mutually recursive call to say, hey, you're going to need something here. You're going to need a parameter. Now, we could wait till later to fill in those question marks. But in this case, I know that once I start looking for a given n, the whole way down the tree, I'm going to be looking for the same n. So n's never going to change. N is always the same value. So I'm just going to keep passing n in all the recursive calls. I can fill it in now. Now, if that's not clear to you now, or if you don't think it would have been clear to you this early, that's fine. You can leave the question marks and fill them in later. I can just tell now that this function doesn't change the n as it goes, so I might as well fill it in now. Okay, now let's see. Start with the base case example. If we find LOE in empty, that's false. That puts a false here, which of course makes sense. If you're looking for something in nothing, you can't find it. Now here's a case that says if we're looking for F3 and F1, we don't find it. If we're looking for F3 and F3, we do find it. So it seems like that when we're looking at an element, there's kind of 2 cases. This is the case where we find it right away. Right there and right there, we find it right away in those 2 cases. And then there's the case where we don't find it right away. So that suggests an if in find dash dash element. And the question is, is the name of this current element the name that we're looking for? So both names are a string. This nice little note here that I put in the template reminds me of that. Is the name of this element the name I'm looking for is the question. One thing about this little note I put in the template, in some other kinds of programming languages and in more sophisticated programming environments, this would be automatically given to you. You could just kind of hover here and it would say, oh, that's going to produce a string. So we're just replicating a feature that you might get in some other languages already. I like putting it here explicitly to help you understand kind of where it's really coming from. We'll delete it now. So let's see, if the name of the current element is the name we're looking for, then what are we supposed to do? Well, we're supposed to produce that element's data. So there we go, we'll just produce its data. And if the name we're looking for isn't the current element, well, what are we supposed to do in that case? Well, these other examples are saying that you keep looking. We got to go look in all the children. In other words, we got to do the natural mutual recursion. And we should follow the standard advice, which is to trust the natural mutual recursion. This is going to go look in the children, and whatever it produces will be the answer. Now let's go down here. Now we're looking at a list of elements. And we don't actually have an example for this. So let's put in an example for this. Let's say check, I'm going to put it right here because it's really a little bit simpler than the D4 example. I'm going to say find element, find dash dash LOE, I mean, in cons F1, cons F2 empty. This is the subs of D4. Okay, this is the subs of D4. So actually, I'm not putting this in the right place. I should really be putting this up here. This is the subs of D4. And I'm finding, what do I want to find in there? Let's say I want to find F2. Can I find F2 in there? Yes, that should produce 2. And we'll add another one. Can I find F3 in there? And the answer to that is false. And now I can really understand that these examples all have a bit more structure. There's really the base case example. There's the has no children examples where we're looking in F. We're not looking in anything that has children. And then this example here is a quite similar example because I'm moving it up here now because it's really an immediate success example. This doesn't go look in the children. So we look in nothing. We look in things that have no children. We don't look in the children. Here we look in lists of children. And now we start looking in things where we have to look at the element itself and its children. So now I've got the examples ordered more in terms of their complexity. And so find dash dash LOE is really kind of here and here. Now let's see. What are these two mutual recursions going to do? These two natural mutual recursions, what are they going to do? This will produce integer or false depending on whether it's found in first of LOE. Let's make that a little bit more compact. If n is found in first of LOE. And this second one will produce integer false if n is found in rest of LOE. Now if we find it in the first, there's no use looking in the rest. We're supposed to find one of them. We don't need to find more than one. So that suggests an if. Now what's the question? Well, this thing produces false if it can't find it. This natural mutual recursion produces false if it can't find it. So, and I apologize for the double negative here, but if it doesn't produce false, that means it found it in the first. So the way I'm going to phrase this question is not false that. And that will mean is it found in the first? Is it found in first LOE? And if it is found in first LOE, well then that's what we want. That value that came back, which is going to be an integer, is what we want. And if it isn't found in the first of the LOE, well then we better go look in the rest of the LOE. That's the natural recursion. Now let me just note this question here, which I phrase as not false, find dash dash element. I could also have phrased this question as open paren integer question mark, find dash dash element dash n first LOE. In other words, I could have used integer question mark instead of not false. And the reason I use not false is it's more general for backtracking functions. When we see other backtracking functions, we'll say false. And the reason I use not false question as open paren integer question mark, find dash dash element dash n first LOE. In other words, I could have used integer question mark instead of not false. And the reason I use not false is it's more general for backtracking functions. When we see other backtracking functions, we'll have this same not false pattern. So let's see, maybe, hopefully, I'm done, and I am. All the tests pass.
Oh, let's see. Hold on.
I'm done, and I am. All the tests pass. Now, why is this called backtracking? Well, let's just step through a couple examples. Let's add one more example to this. We'll put it up here. Let's look in D6 for D6. And when we go to the first of the subs, which is we still have to a failing node with no sub-elements. Those are called leaves. Branches looking for what we want.
Alright, we did one. So let's review our homework. Problem one. Alright. Problem two, design a function that produces the list of all the course numbers. Oh, yeah. Oof. Okay. think we're about wrapped up. I think we got so far we want to get done today. We have a minute left on the clock. Mhm. Um, all right, I think I'm gonna call it. So yeah, appreciate y'all pulling through. Whoever came on, and yeah, see you guys soon for another stream. I think streaming definitely makes me a bit more productive. I feel a little bit peer pressure to stick to the tomato timer, the 25, 5, 25. So we'll keep this up. Um, we'll keep this up for sure. So yeah, I'll see you guys another